A free body diagram is a simple representation used in physics and engineering to analyze the forces acting on an object.
It simplifies a complex physical situation by isolating the object of interest and showing all the forces acting on it as individual vectors.
A vector has both size, or magnitude, and direction, whereas a scalar only has magnitude.
A free body diagram helps in understanding and visualizing how different forces are affecting the motion of an object.
Let's take a quick look. Here we have some water, a boat on the water, someone is happily sailing along, and there's the mast and sail. There we go. Here is a very simple diagram, and remember, free body diagrams use simple representations. Now we need to add some forces in. Let's draw 4 forces on this diagram. We have one going this way, one going that way, one coming down, I'm assuming we know what that one is, and one going up. This is a free body diagram showing the forces acting on a boat. What are these forces? Well, to push the boat along, we have a driving force. I guess the wind pushing in the sail. But because the boat is moving along, we're going to have friction. Now remember, friction is a force that opposes motion. So it's acting back in the direction, the opposite direction to the driving force. Gravity is always acting, trying to pull the boat towards the center of the earth. But you'll note the boat isn't sinking, it's not actually going towards the center of the earth, and that's because we have a supporting force. The supporting force in this case is the buoyancy of the water. A supporting force is essentially any force that will stop an object moving towards the center of the earth. So we've labeled the forces there. That is a free body diagram. Let's take a quick look at another example. Here we have a block and one force there, another force there. Here's a free body diagram. Now you'll note in this case the arrows are different sizes. Force is a vector. It needs both a size or magnitude as well as a direction. Well, arrows are great at showing the direction, but the length of the arrow is indicative of the size of the force. So if we knew the sizes, we could also label those. Maybe this is a 10 Newton force, and the force from left pushing to the right is bigger. Let's say, I don't know, maybe 25 newtons. It is bigger. We can tell that because the arrow is a longer arrow. The length of the arrow indicates the size of the force. So what we can do is add these two forces together. When we do vector addition, we put one and then we add the other one, the tail of the other force, to the head of that force. So essentially we're coming back this way. Now, those 10 newtons of force are going to cancel out 10 newtons of the bigger force, and that will leave us still with 15 newtons of force to the right. This is what we call the resultant force, or the net force. So we can add these two forces. The bigger force is going to win out, and the block is going to be accelerated towards the right, with a resultant force of 15 newtons. Remember, an object will not change its motion unless acted on by a resultant force. In this case, yes, we have a resultant force of 15 newtons. So the block is going to be accelerated towards the right. What about people jumping out of a plane? For some strange reason, some people like to do that. They jump out of a perfectly good plane, which, as you can see, I'm really good at drawing. Cockpit, some windows. There we go. There was a perfectly good plane that someone had this great idea. They decided to jump out of it. What forces are acting on the person now? Well, we have gravity acting down with a force of 9.81 newtons. So that person, the instant they jump out of the plane, they will be accelerating towards the ground. But as they get faster and faster, we will have another force increase, and that will be the air resistance. At the moment, they've just jumped out of the plane. That air resistance is less than the force of gravity. Actually, let's just label that the air resistance. But it is less than the gravity, so the person will be accelerating. If we did a vector addition, the gravitational force is more than the air resistance, so our net force is going to be down. The person will accelerate downwards. But as they get faster and faster, that air resistance is going to increase and increase. Eventually, it's actually going to be the same size as the force of gravity pulling down. What we have now are balanced forces. If we do a vector addition, we've got this force going up, we've got this force coming down. Because they are the same size but opposite direction, they will essentially cancel out, and our net force, our resultant force, will be zero. We don't have a resultant force, so there will be no change in motion, which means the person is now going to fall at a constant velocity. Now, in terms of something falling towards the Earth at a constant velocity, we call this terminal velocity. For a person, the terminal velocity is about 200 kilometers per hour. So you'll accelerate, you'll speed up until you get to that speed, but then once air resistance is equal but opposite to the force of gravity, you won't actually get faster. You'll just keep falling at 200 kilometers per hour, which is not really a good speed to hit the ground at. Luckily for this person, they had a special backpack on, and that backpack had something in which we call a parachute. They weren't an idiot just jumping straight out of a plane. They had a parachute, so that's great. So they open the parachute. What happens now is this. Now, just as they've opened the parachute, the air resistance, the friction, is actually more than the gravitational force pulling them down. So we do our vector addition, and we find that our net force is going to be upwards. If we take one vector, let's do the gravity one first. It really doesn't matter which you do first, but we'll start with gravity and then we'll add the air resistance, and we can see the gravitational force will cancel out some of the force of air resistance, that frictional force, but we're left with the force going upwards. So this person is actually going to accelerate upwards. Does that mean they are moving upwards? No, it doesn't. They're actually still moving down. They're falling towards the ground, but they're slowing down. Accelerating upwards when you're moving downwards, it means you're going to slow down, you're going to slow down, slow down, slow down. Eventually, they will slow down and their air resistance will decrease, and eventually it will be back down to the same amount of force upwards as the gravity coming down. So they're now falling at terminal velocity again, but it will be a slower terminal velocity. One that is in fact much safer to land from. So there's a quick look at using free body diagrams.
Don't forget to subscribe and like and comment.